So today start a new chapter, magnetism and matter. Okay, so magnetism and matter. Magnetism and matter. Okay, so first we discuss some common ideas regarding magnetism. Okay, some common ideas, some common ideas regarding magnetism. Okay, the first common idea is that the earth behaves as huge magnet. Okay, if earth behaves as a huge magnet, so obviously there is a magnetic field. Okay, and there is a two pole, one is north pole, other is south pole. So the if that earth behaves as a magnet, so there is a two pole obviously, and the pole or the magnet of pole, there is a two pole, south pole and north pole. This south pole in case of earth is called geographic south. Geographic south. And the north pole of that magnet means the earth have north pole, because earth has a magnet, so this north pole is called geographic north. Geographic north. That's two important points. So earth has a magnetic field line, so there is a two poles, and earth have two poles. These two poles named as geographic south and geographic north. Okay, there is some little bit difference there. Why is called it geographic north and not called directly only north? Okay, there is some difference here. Okay, like discussion some difference here. There is some difference between earth and bar magnet direction oriented. Okay, and number two, when a bar magnet is freely suspended, okay, there is a bar magnet. When a bar magnet is freely suspended, and the point of the north and south direction, if there is a two direction, north direction and a south direction, if I freely hang that bar magnet, this is a bar magnet, and a bar magnet, we suspended. The point of the direction of geographic north is called north pole. Okay, and geographic north is called north pole, and there's another pole is the tip of the direction is geographic south is called south pole. Okay, so this is a bar magnet. So there's a bar magnet. So geographic point of the geographic north point of geographic north. Geographic north, and tips of the points of tips in that direction of the south is direction of south is called geographic south. Okay, clear? South pole direction. Okay, south pole. Okay, so now the third point, point number 3, that's an interesting point, is a like pole. So if I consider a magnet has two poles. We know that from school, 6, 7 class standard. We know there is a two pole, one is the north pole, other is south pole. These two pole, okay, there is a force, okay, magnetic force. If like pole, so is the north and north is called like pole, or south and south is called like pole. So if a north and north is like poles, so there is a repulsive force. There is a force. There is a repulsive force. Okay, and unlike pole, like a north versus south or south versus north, there is attractive force. Clear? Yeah, north pole and the south pole. If someone try to break that magnet, if someone to break that magnet, and magnet are getting in two pieces, suppose there are two pieces. The question is arising, if a magnet is broken down into two parts, so previous there is a one single, that is a north, suppose there is south. If I break that here, So is a magnet a monopole? This is a question arise. क्या magnet एक monopole की तरह treat करेगा? No, answer is no, because no monopole exists in magnet. If I break that magnet into pieces, so that is the north and opposite side is get south, and the south opposite side will get north. Okay, so this small piece of magnet and break down from original piece of magnet, this small piece also treated as a magnet. This small piece also treated as a magnet, but the force is little bit weaker than previous. Okay, force is weaker. So means the final conclusion is that these 4 points, no monopole. Magnet has no monopole. Always dipole are in present. Okay. Clear? These are the basic 4 common ideas regarding the magnetism or magnets. Okay. Here, that next part we discuss the magnetic field lines. The magnetic field lines. So, magnetic field line. That's an important concept. If there is a magnet, there is a field, obviously there is a line, and this line is called magnetic field lines. Okay, suppose there is a bar magnet here. Suppose you place a bar magnet here. There is a north pole, that is a south pole, and the field line released from north and ending to south. Okay, and that's not actually end here, and obviously goes in that. Okay, so like this. Clear? So magnetic field line is a closed line. Is a closed loop. Is a closed loop. Very important. Magnetic field lines is a closed loop. Okay. That's the direction of B. Magnetic field is the direction of B. Okay. Now another important point. If there is a bar magnet also, that is a bar magnet. Now you can use a solenoid here. Suppose solenoid is look like this. Solenoid is like this. Dotted line is behind that. Okay, back portion of the solenoid. Okay. Now the current direction. Suppose there is a direction of current I. There is I. The current direction. Okay. Now there is a current direction. The thumb is represent current. So there is a magnetic field lines. Okay. Suppose the current direction is thumb represent current. So drawing like this is thumb represent current, and curl of other 4 finger is that curl represent the magnetic field. Okay, so the field is look like this. Now this field is inside. Okay, drawing is not good actually. Okay, that is a closed line, obviously closed loop. Okay, so that's the direction of B. It's obviously magnetic field. Okay, there is a closed line here. Okay, see, there is an important point here. This solenoid also treated as a magnet, bar magnet. This solenoid, this know that solenoid and treated as bar magnet. You know the concept, okay? So here is the important factor. If I choose a to path here, suppose choose some close path. Okay, well, closed region here. There is a closed region. I choose another closed region here. That is the region number 1. That is region number 2. And I see that the line density, okay, field line density is both are area be the same. If this area and this area be the same, and you see that there is a two field crossing this region 1 and one field is crossing the region 2. So the line density, so line density of region 1 is greater than line density of region 2, because there is a two line crossing that region 1, that is one line, that is 1 by suppose a 1 by a, suppose 2 by a, obviously 2 ratio 1. So line density means number of line, some there is a region, get line density is far more better here. So if line density more, so magnetic field obviously the more here. Okay, there is a weak magnetic field here. Okay, there is a stronger magnetic field. So that is stronger magnetic field in region 2 than region in region 1 than respect to region 2. Region 2 is weaker magnetic field. Okay. Now these two are the magnet. Bar magnet also treated as a obviously bar magnet also treated as a magnet because there is a magnetic present here. Solenoid also treated as a magnet because there is a magnetic field obviously at the direction here, and there is a two charge, like suppose a charge plus and minus. So there is a electric field, and obviously electric field starting from plus and ending to minus. Okay, ending to minus. Okay, that's the electric field. There's the electric field E, because there is a single charge. Okay, a static charge create an electric field. We know that the concept static charge create electric field. Here there is a magnetic field created by the moving charge. You remember that key point. Okay, याद रखना कि पीए का अगर सिंगल चार्ज होगा तो सिंगल चार्ज create electric field. If their charge is moving, that the moving charge, obviously the moving charge create a magnetic field. Okay, thus there are some properties of magnetic field lines. Okay, in board exam there is some 1 or 2 marks question you get. Okay, what is some properties? Write some properties of magnetic field line. Properties of magnetic field line. Properties of magnetic field line. So property number 1. Okay, so magnetic field line is a closed loop. Okay, the magnetic field line is a closed loop. You see that. Okay, here is a magnetic field line is a closed loop. But if you consider electric field line, that's not closed. Not closed. In case of E, E is not closed. Okay. Now the another point. Okay, so if you draw a tangent at any point, okay, tangent at any point on magnetic field, so that's the tangent. This tangent represents a magnetic field B. Okay, that's obviously this blue color represents the line, and if you draw a tangent and in that direction, obviously there is a in that direction the tangent, this tangent represent the magnetic field. Okay, clear? So always important, the magnetic field is a vector field. So vector field means there is a magnitude obviously, and that we know that the SI unit of magnetic field is Tesla. Suppose there is a 2 Tesla, here also say that 2 Tesla, but difference is there is a direction is different, because magnetic field is a vector field, that's the direction is different but magnitude be the same. Okay, so magnetic field always be the vector field. Clear? And another important point that is we discuss here, the stronger magnetic field and weaker magnetic field region. So, okay, so that important point here. If you draw a tangent, if you draw a tangent, if you draw a tangent at any point on the magnetic field line, obviously electric field will be same. Magnetic field lines, you get magnetic field B. Obviously that's a vector field. Okay. Now there's another important point that stronger magnetic field and weaker magnetic field we discuss here. Okay, the stronger magnetic field is number of field length per region is greater than number of field length in smaller region. Okay, less number of magnetic field across the same region. If there is same region, so okay, obviously is a magnetic field at region 2 is greater than magnetic field of region 1. Okay, because there is a one field crossing that region 1 and two field crossing the region 1 and one field crossing the region 2. That's why the line density, field line density is more. If field line density is more, so magnetic field obviously will be more. Okay, and the last point, number 4, field line do not intersect each other. Okay, the same as electric field. So the same field line, okay, these two field line, any other field line do not intersect each other. Field line do not each other. If they intersect each other, if so, suppose you can see that there are two magnetic field lines. These are the B1 and these are called the B2. Okay, and these two magnetic cores intersect each other, or say that is the both are with the same, these same. Okay, so you get two tangent at the same point, or say that is B2 here, two tangent at that same point. Two tangent at the same point is not possible here. Okay, because at that point you see that if they are crossing here, suppose if they're crossing here, at that point direction here, this direction obviously the here, that is called B1, that is called B2, there's a direction be the different. Okay, at the same point the direction be the different is not possible. Okay, because that at that point a single point represents a single magnetic field direction. Okay, not multiple magnetic field direction, because the direction is different, then the magnetic field is vector field, so the total value be the difference here. Okay, that's why they do not intersect each other. Okay, clear? Now we discuss the bar magnet as an equivalent solenoid. That's an important calculation here. The bar magnet treated as equivalent solenoid. Okay, suppose there is a call conductor here. Suppose there is okay, the line is not perfectly oriented here. Okay, this is the back side. Now the coordinate. Okay, front. Okay, here we draw a very thin length here. Differential. Okay. And suppose this length be the x and this differential length say that is a dx. Okay, and length be suppose that is a L and total length suppose of the conductor is a 2L. Okay, and the distance of R from here, suppose magnetic field calculated at here B, mm, that is okay. Now that's the radius of the conductor. Suppose radius be that A, and this radius also be here be A. So now join this line. Okay, from Bharat-Savart's law, obviously from now erase that. Okay, and this line here, and that say that is length is R. Okay, this length is R, and apply the Bharat-Savart's law here and calculate the magnetic field at that point P. Okay, before the application of Bharat-Savart's law, from we know that magnetic moment. Okay, so magnetic moment mu that is equal to, we know that is NIA. Okay, N is the number of turn, I is the current passing through the conductor, A is the cross sectional area. And then now the Bharat-Savart's law dB at point P that is equal to, we know that application of Bharat-Savart's law that is mu 0 I. Okay, some the value is here the radius square. The radius be suppose that A square by twice the distance from here to there, that distance to there, that is equal to that length is x, that is R minus x, that is R minus x. So R minus x whole square. Okay, and another the radius a square. Okay, and the another info sorry, whole to the power 3 by 2 obviously, and that another info is the number of turn here. Okay, so if I choose a very small here, so that is turn density, that is n, n with the number of turn n by small length dx. So if turn density get n dx, the n equal to that is n equal to n dx. The turn is very important. Okay. Now solving this with by integration here. So you get b here. Get b integration of db be the b, and there is some length here minus L to plus L. That's the length obviously. And now I apply some condition here. If R is much greater than X, and obviously the R is much greater than L. So what will happen, that is equal to mu 0 I a square n dx by obviously the R only here. So R square whole to the power 3 by 2, 2 to the cancel, that is the R cube. Okay, now next we get b here. So mu 0 I a square n, okay, by r cube, the outside the integration, these all are the constant, mu 0 I a square n by r cube minus L to plus L dx. That's okay. Now the b mu 0 I a square n by r cube. Now integration of dx with the x, so upper limit minus lower limit, so L minus of minus L, so finally get it twice L. So we get expression B mu 0 I a square n to L by R cube. Okay, so you see that very carefully. These are the expression. Okay, now oh, the equation here. The equation sign sorry B mu 0, suppose you multiply by 4 pi, mu 0 by 4 pi I. Okay, now replace the mu, that is equal to NIA. So if I n, that is equal to the total length, that is 2L. So n times 2L, that is n density times 2L, get total n. So these n 2L represent the capital N. N 2L represent capital N, and here the I, and that is a square, and if multiply the pi here, so another pi upside, that is here a square. We know we need, that is a 4, we have 4. Sorry, there is a mistake 2 here. So that side, this is 2 outside the integration 2, that side 2 here, 2 here, that's where the 2 here, 2 4 cancel 2. So finally get B equal to mu 0 by 4 pi, that is capital N area, and that is I, that is equal to mu. Okay, and is a 2, so 2 mu, obviously there is a vector 2 mu. Okay, there is obviously R cube by R cube. Okay, that's a magnetic field expression. The bar magnet also equivalent as a solenoid. Okay, here we get the final expression of B. Okay, that is equal to mu 0 by 4 pi twice mu by R cube. And these are the final expression, and these say that is this final expression represent the bar magnet also as a treated as a equivalent a solenoid. Okay. So today in the class here, if you have any doubt in that portion, always ask in comment section. I will try to give the answer. Okay. Next class we discuss a dipole in a uniform magnetic field. So today the summary is the class here. So today we summary is we start a new chapter, that is magnetism and matter. Some common ideas regarding the magnetism. There are two or three basic common ideas discussed here. Magnetic field line concept. There is very important, the difference between electric field and magnetic field. What is the similarity between these field lines two? And here the calculation. Bar magnet also treated as a equivalent a solenoid. Okay. So today in the class here. Thank you.